Okay, Math 31, so we're going to talk about section 10.4 area in terms of limits. I already introduced this a little bit in the last lesson in terms of h is approaching 0 using our trapezoid formula, but I'm going to do it this time using sigma notations and rectangles. So this is, again, another very popular way to do it. So back in limits, we did our sigma notation, so if you remember what it was for a general term or function. So let's just try an example remembering what our sigma notation was, and then I'll show you how it's going to apply to this one. So here we have sigma notation is where it's the sum, n equals 1 is our starting point. So this is the number of terms. This is our function, so whatever it is, and we're starting at 1. So for this example, we have 4 terms. We're starting at 1, and my equation is 3 to the power of n minus 2. So to do this, all I'm going to do is plug in 3 to the power of 1 minus 2 plus 3 to the power of 2 minus 2 plus 3 to the power of 3 minus 2 plus 3 to the power of 4 minus 2. So I have my 4 terms. Now this is going to be 3 to the power of negative 1 plus 3 to the power of 0 plus 3 to the power of 1 plus 3 to the power of 2. So I get 1/3 plus 1 plus 3 plus 9. I get 13 over 3. And that's all it is when asked to evaluate something with our sigma notation. Now, there's a little bit difference when we're going to introduce something called series. So if you remember series and sequences all the way back in 20-1, here we have the terms. So T1 is equal to term 1 plus term 2 plus term 3 all the way to Tn, which is our general term. These properties are what you're going to be given on an exam. You wouldn't have to memorize these. And so all you need to know is a couple of these formulas and how we would expand using I. So I'm just going to skip to the next one. So what you need to know for sigma is this one right here. So knowing what I and what I squared are equal to, and I'll write out what I squared is equal to. It's n plus 1, 2n plus 1 over 6. And that's about as far as you're going to go. So what this means is when I have this guy right here, I have 4 times 4 plus 1 all over 2, which works out to be 4 times 5 divided by 2, which is 10. So this would have a value of 10. And what that means is if I started with 1, I had 1 plus 2 plus 3 plus 4. There are my 4 terms starting at 1, and this equals 10. It's the same thing. Same if I were to do this. I'd have 1 squared plus 2 squared plus 3 squared plus 4 squared. Or I can use the general formula that somebody so nicely came up with, and all I have to do is plug in n, which is 4. 4 plus 1, 2 times 4 plus 1, all over 6. And I get 4 times 5 times 9 all over 6, which works out to be 180 over 6, which is 30. And if I were to add all these together, we would get 30. So that's how we use our sigma notation. Obviously, it's going to get a little bit more complicated than this, but these are 2 of the ones that you need to know. I'd put them on a formula sheet, and I would have a look at those. Now, I'm going to show you how we're going to use this to find area. So we have this big, long value. So we already did method 1 when we proved f of b minus f of a using our area and limit as h approaches 0. This is our second method that we're going to talk about. So if I have this diagram here, using my sigma, we're going to say that n is approaching infinity. So we're saying that the sum of all of these rectangles is going to give us an area. So what I want to show you is where this is coming from. So it's important, oh my goodness, that as the number of subintervals, this is terrible, from A to B, I'm going to increases. Okay, so the more little rectangles we have, the approximation gets better. Okay, so the more little subintervals that we have. So I'm just going to explain what all of these are. So delta x, here, you could see is the width of all of these little rectangles that we chose. N is how many rectangles we want. And as I just mentioned over here in this awful writing, is that the more we pick in terms of n, the better off it's going to be. And that's where we're saying the limit as n approaches infinity. So we want a million, trillion different. The more we get it, the smaller these rectangles become, the more accurate our area becomes. If I wanted to look at what x1 would be, so if I chose something here and I called this one x1, how would I find it? It would be a plus delta x. If I wanted to know what x2 was, so that would be this guy right here, that would be a plus 2 delta x. If I wanted to know what x3 was, that would be a plus 3 delta x. So you can kind of see a pattern. So xi is just equal to a plus I delta x. And that is how we're going to get our height. Okay, so in here, this is the area of a rectangle where you have your width, oh my gosh, width times your height, which we just said would be this one, xi. And it would be f at xi. So let's just try to go through this. Hopefully this won't be as messy. I'm going to do it on a notebook because this is not working on the PowerPoint. Okay, so find the area under the curve f of x is x squared from 0 to 3 using sigma rectangles limits as n approaches infinity. Okay, so here's my graph. There's my x squared. I want to go from 0 to 3. And I'm going to divide this up into a whole bunch of rectangles. Remember, the width is delta x, and the height of each is going to be that f of xi. So we're going to set up that the area to 3 is the limit as my rectangles goes to infinity, so the number of them that I use. N is just arbitrary, but we are going to start at I is equal to 1. F of xi delta x. So remember, this is our length times our width of each rectangle. So let's go ahead and find all of those values. So first off, I want to find out what delta x is, and that's b minus a over n. So delta x is 3 minus 0 over n, which is 3 over n. So the width of each one of my rectangles is 3 over n. So if I chose I only wanted 2 rectangles, the width would be 3 over 2. If I wanted 4 rectangles, it would be 3 over 4. 2, let's find xi, which we said is a plus I times delta x. So the height, a, we're starting at 0. I, we just leave as I, and delta x is 3 over n. So xi, that we're going to find our height, or the length of all of our rectangles, is just going to be 3i over n. Now, the last thing that we want to find is f at xi, which is going to be, remember, it's x squared. So we're going to have that 3i over n squared, which is going to be 9i squared over n squared. Okay, so now we're going to plug it into our limit. So our area is going to be the limit as n approaches infinity of my sigma rectangles. And I'm going to have my my f of xi, which is 9i squared over n squared, times my delta x. So this is f of xi, and this is delta x. And this is going to be 3 over n. I'm going to expand this, the limit, as n approaches infinity. I'm going to have, 27i squared over n cubed. Now remember, n cubed, like that's just a number. N and 27 are just a number. So as I pull this out, I'm going to have 27 over my n cubed, because n could be anything, it's just a number. And then we have just I squared here. So we want to try to always get I or I squared by itself. And now I'm going to replace what I squared was equal to. So I now have the limit as n goes to infinity of 27 over n cubed. This, I now replace it with n plus 1, 2n plus 1 over 6. I'm going to simplify this. The 27 and the 6 reduce each by 3, and I'm going to get 9 over 2. This n and one of these cancel, so I'm left with n plus 1, 2n plus 1 over n squared. Now remember, what do we do to do limits to infinity? We are going to expand our bracket to get 2n squared plus, what do we get? Plus 2n plus n, so plus 3n plus 1 over 2n squared. I'm going to distribute my 9. I'm going to get 18n squared plus 27n plus 9 over 2n squared. And remember, to evaluate limits to infinity, we divide everything by that highest term degree. And we get, this becomes 18, this becomes 2. Remember, this one goes to 0, this one goes to 0. So I'm going to get 18 over 2, which is 9 units squared. And that is how we do our sigma notation to find our values. I'm going to show you using the other method, just for fun. Okay, so for this example, f of x is x squared, and we were going from 0 to 3. So remember what I said is, first find the antiderivative. We get x cubed over 3 plus a constant. Then we would go from f at 3, area at 3, would then be f at 3 minus f at 0. When I plug in this 3 cubed over 3 plus a constant, 0 cubed over 3 plus a constant, my constants cancel. I'm left with 27 over 3, which is 9 units squared. So obviously a lot less work using the antiderivative or using this first method that we talked about in the last lesson than using limits, using sigma notation, but you have to know both. And that is it.